Hello and welcome to this video about nuclear decays and reactions. We're going to look at what alpha, beta, and gamma decay are, and how they're different and similar. What is transmutation? We'll compare and contrast fission and fusion, and we're going to look at the relationship between mass and energy. Remember, when a nucleus is unstable, it can decay, and we are going to look at three of the ways that it could decay. It could emit an alpha particle. What's an alpha particle? Well, an alpha particle kind of looks like this. It looks a lot like the helium atom. It's a particle with two protons and two neutrons. It's very high energy, and it is essentially the helium nucleus. So the symbol for an alpha particle would be helium, indicated here by the symbol, as well as the numbers 2, telling us that it has two protons, and 4 means that it has a mass of 4, a total of 2 protons and 2 neutrons. Alpha can also be written like this, the Greek letter alpha. Sometimes the alpha particle is abbreviated that way. And again, its mass is 4 atomic mass units. It has a charge of +2 because it has 2 protons and no electrons to balance that charge out. Because it's so large, it can simply be stopped by a sheet of paper. So an alpha particle isn't going to penetrate your skin even. The only way it would cause damage to you, and it could cause considerable damage, would be if it were to enter your lungs, if you were to breathe it in, because it cannot penetrate your skin. Another way the nucleus can decay would be to emit a beta particle. And a beta particle is essentially an electron. It's a very high energy electron, a lot of energy. We write the symbol like this, or we can also abbreviate it with the Greek letter for the second letter of their alphabet, beta. It's sort of a curly little bee with tails on it. And of course, this has a tiny, almost negligible mass. There is some mass, but it's 1/7,000th the mass of an alpha particle, very tiny. And its charge is a -1. It can be stopped by a sheet of aluminum foil that's about 3 millimeters thick. So a beta particle can penetrate more matter than obviously an alpha particle. It's smaller. A beta particle would be able to travel through your skin, through most of the tissues in your body. It would actually take a sheet of aluminum at least 3 millimeters thick to be able to stop a beta particle or absorb most of that beta radiation. So far, you've learned about 3 fundamental forces in nature: gravitational force, electromagnetic force, and the strong force. The fourth and final fundamental force is called the weak force, and it causes beta decay. It's similar to the strong force in that the weak force is very short ranged. It is also weaker than all of the other fundamental forces except for gravity. The weak force can cause neutrons to decay into protons inside of a nucleus if the neutron to proton ratio is too high. When this happens, the nucleus emits a beta particle or an electron. And the last kind of nuclear decay we're going to look at would be gamma rays. They are extremely high energy and high frequency electromagnetic waves. Lead bricks or other heavy materials are necessary to stop it. They're usually emitted from a nucleus during alpha decay and beta decay as well. Gamma rays have no mass, they have no charge, and they travel at the speed of light. Their symbol would be the Greek letter gamma. And obviously, when a nucleus loses energy but no particles, that's where you get these gamma rays coming off of the nucleus. This is just an image showing the levels of penetration from the different kinds of radiation. All 3 kinds of radiation can damage biological molecules and can lead to illness or disease or improper cell functioning. Transmutation is a word that we use to describe the process of changing from one element into a different element. And this occurs during alpha decay or beta decay, where we have, here's an example of alpha decay. An alpha particle is being given off, and we start out with plutonium-239, and when an alpha particle is given off, we end up with a different element, uranium-235. That's because two of those protons are wrapped up in this alpha particle. Also notice that the mass, we have 2 protons and 2 neutrons, so the total mass on our uranium particle should go down by 4 atomic mass units. Here's an example of transmutation by beta decay. We have this hydrogen isotope here, and it is giving off a beta particle, and it is being going through a process of transmutation and changing from one element into another. Remember, conservation of charge holds true always in these cases, as well as conservation of mass. But the total charge before the radioactive decay is always equal to the total charge after the radioactive decay. Now let's take a look at fission versus fusion. And you guys have all already studied this probably before. Fission is represented here in this picture. We have a large nucleus that is breaking off into smaller nuclei. Fusion would be the opposite. We have 2 nuclei that are fusing together into one larger one. So let's take a closer look at nuclear fission, the process of splitting a nucleus into 2 or more smaller nuclei. And whenever a nucleus emits radiation, some energy is released. However, the amount of energy that's released during that nuclear decay is very small compared to the amount of energy that could be released during nuclear fission. Huge amounts of energy are released here. Scientists can cause fission to happen by bombarding this large nucleus with neutrons. This diagram shows the nuclear fission reaction for uranium-235, and that is the type of atom that was used in the nuclear bomb that was dropped on Hiroshima during World War II. And this is the type of reaction that occurred. Other fissionable materials would be plutonium-239. Uranium-233 also will undergo fission. You can see that in addition to 2 smaller nuclei, some of the products of nuclear fission are also additional neutrons. These neutrons can then strike other nuclei in the sample material. Here we have more unstable nuclei, and they can be split as well. This causes what is called a chain reaction. It's a series of repeated fission reactions caused by the release of additional neutrons in each fission reaction. If a chain reaction is uncontrolled, then an enormous amount of energy is released all in one instant, like as in the case of a nuclear fission bomb. However, if a chain reaction is controlled, if materials are added that absorb these extra neutrons, then the reaction can be controlled and it can be a useful reaction, and that's how nuclear power plants are operated. So now let's take a look at nuclear fusion. Fusion reactions release even more energy than nuclear fission reactions. And in a fusion reaction, we have 2 or more nuclei that combine to form a nucleus of a larger mass. Here is an example of that. Now, you can think in your brain logically, well, in order for nuclear fusion to occur, the nuclei have to get really close to each other. But remember, we've just been talking about the positive electric forces, the charges between the protons, and those forces are going to be repelling each other. In order for two atoms to fuse, the nuclei have to have enough kinetic energy to overcome that repulsion between the protons. Remember that kinetic energy of atoms increases when their temperature increases. So the kind of temperature we're talking about for fusion to occur is millions of degrees Celsius. That's when the nuclei are moving so fast that they can get close enough for fusion to occur. And those kinds of extraordinarily high temperatures are found in the centers of stars, such as our sun. So these kinds of reactions go on in the sun. Here is an example of a series of fusion reactions that occur inside the sun's core and provide it with its power. Just a little FYI, a neutrino is represented here, this sort of a cursive V-looking symbol. And it's a tiny, almost massless particle. A positron is simply a particle that has the charge of a proton, but the mass of an electron. Now, thinking about these fusion reactions that are taking place inside the sun, you'll notice that no matter is ejected out of the sun, but the total mass of all the particles in the reaction is greater before the reaction than after. How can that be true? How can you have less mass after a reaction if no matter is leaving the sun? Well, according to the theory of special relativity, a tremendous amount of energy is the same thing as a small amount of mass. Energy and mass are related by this equation here. You've probably all seen that E equals mc squared, where energy, E is energy in joules, m is mass in kilograms, and c is the speed of light in a vacuum, which is 3.0 times 10 to the 8th meters per second, and that is squared. Let's do a little example problem. If the sun emits about 3.8 times 10 to the 26th joules of radiant energy every second, how much mass does the sun lose every second due to this energy emission? I'm going to write down the equation that I'd like to use, E equals mc squared, and I know values for E and for the speed of light in a vacuum, which is c. And I want to solve for m. M is my unknown. When I plug the values into this equation, I'm simply substituting this value for E, this value for C, and don't forget to square the C. I can then do the math. If I divide both sides by this term, I can isolate m, get my variable on one side of the equation. And when I punch all of this correctly into my calculator, I end up with a mass of 4.2 times 10 to the 9th kilograms. That's roughly the mass of 12 Empire State Buildings. That's a lot of mass that the sun loses every second. Some advanced ideas. What is electron capture? Find an example of this kind of nuclear transformation. Also, who chose alpha, beta, and gamma to name the different kinds of radiation? Why and when were these names chosen? I look forward to seeing what you come up with, and we'll see you in class.